good, good. طيب. This is the outline of the presentation. So let me, talk here about the MIPS instruction set architecture. Okay, so what do I mean here by instruction set architecture? The instruction set architecture is a critical interface between the software and the hardware. So all the software is translated into the instruction set of a given processor, and the hardware executes these instructions. So the software is going to translate, is going to be translated into the architecture of a given processor, and the hardware is designed to implement these instructions. So when I say instruction set architecture, it includes the following: the instructions, how they are defined, and their formats, okay, in binary. So I'll talk about this in a great detail. The data types which are supported by the architecture, okay, whether the architecture supports, let us say, integers, characters, floating point numbers. Characters are encoded just like integers. So their encoding, their representations, floating point numbers have a different encoding and different representations. So I'll talk about this separately later. The architecture defines the programmable storage, the registers that can be used by the programmer, okay, and they are accessed directly by the instructions, and the memory, which can also be accessed, okay, by specific instructions that are defined in the architecture. The addressing modes, how to address instructions and data in memory, and how to handle exceptions like overflow and other types of exceptions. So all of these are defined by the instruction set architecture. Now, there are different architectures. There is no universal architecture for all computer systems. Intel has introduced the 8086 architecture back in 1978, and this architecture evolved over time. So Intel has extended the architecture from 16-bit, it was originally 16-bit, to 32 bits, and then to 64 bits. And then it has introduced a variety of processors, but all of them implement the same architecture, the same instruction set. MIPS has a different architecture. It was introduced in 1986, starting with MIPS 1, then MIPS 2, and then we have the MIPS 32-bit and the MIPS 64-bit. So these are essentially versions of the MIPS architecture. And then we have the ARM architecture. It started as a 32-bit architecture back in 1985, but then recently it has been extended to a 64-bit architecture. And there are different versions of the ARM architecture. Now, MIPS and ARM are very similar architectures. Intel is different. It's like studying different high-level programming languages, except that these are the architectures, okay, of real processors. Okay, so when we study assembly language, we're going to study the instructions and the programmable storage, how to write programs at a low level. And it has a one-to-one correspondence with the machine instructions. So let me talk about the details. Okay, let us start. Okay, first, the instructions. The instructions are the language of the machine. And in this course, we are going to study the MIPS instruction set architecture. Please interrupt me if you have any question. Okay, if you feel that something is not really clear, please interrupt me. So in this course, we are going to focus on the MIPS instruction set architecture, and it is known as a reduced instruction set computer. Okay, and the abbreviation is RISC. The alternative is a complex instruction set computer. An example of a complex instruction set computer is the Intel architecture. Now, the MIPS architecture is simple, it's elegant, it has a simple design, and it is very similar to many RISC architectures that were developed in the mid-1980s and 90s. And it is still being used until today. It's popular and used in different products, okay, like, for example, Silicon Graphics, ATI, Cisco, Sony, and different products, okay, use the MIPS processor. MIPS was very popular, especially in the 1990s, okay, on desktop workstations. But today, people use the Intel architecture. So the Intel architecture is very popular on the desktop and personal computers, but the ARM architecture is more popular in the let us say in the cell phones, okay, in some other products, and also is competing with the Intel x86 architecture. So these architectures were defined, okay, to last for many decades, okay, and of course these are they are similar and different. They have similarities and differences. So we're going to focus in this course on the MIPS instruction set architecture. Do you have any questions, students? Everything is clear?
Yes, Doctor. Yes.
Okay. Right. So
I have a question.
Yes, go ahead.
Can we program, for example, Intel processor using MIPS or?
No, what you have to do is that you have to use the instructions of the computer. So if you are programming directly in assembly, the assembly language is machine specific. Okay, so it depends on the architecture of the processor. So you have to use the exact instructions. So the architecture varies from one processor to another one. So the Intel architecture has a different assembly language than the MIPS architecture. And the MIPS has slightly different instructions than the ARM and so on. So that they have similarities, but also they have differences. Okay, so let me talk here about an overview of the MIPS architecture. It's shown in this slide. So we have the main processor, okay, and this is what is known as the integer execution unit. It has, or the execution and integer unit. It has 32 registers from, they are called general purpose. You can use these registers. These registers exist in the hardware inside the CPU, and they are numbered from register 0 to register 31. Now, register 0 is a special register which is hardwired to 0. I'll talk about it later and see the importance of having a register which is always 0. But the other registers from register 1 to register 31 can be written, can be modified. You can read them, you can write them, okay, you can use them in programming. Now, these registers, okay, store data, okay, integer data. So this is why it's called an integer unit. So you can use them to store integer values as well as memory addresses. An address, okay, itself is like an integer, okay, and you can use it to address memory. There is an ALU, which is the arithmetic and logic unit. This ALU is used to execute the instructions. The ALU is going to read registers, typically 2, and then is going to write the result into a destination register. So any register can be read, and any register can be written except register 0. It cannot be modified. There is an integer, okay, multiplier divider specifically for integer multiplication and division. And this integer multiplier and divider, this special execution unit, writes 2 special purpose registers, low and high. And you can, of course, transfer the values of low and high into general purpose and vice versa. Okay, so this is what we call the integer unit. There is also a floating point unit. this floating point unit has a separate set of 32 floating point registers, and it has a floating point arithmetic unit. Now, floating point data has a different format than integer data. We are going to study in this course floating point numbers and floating point arithmetic in great detail. And there is in the hardware, there is a special floating point unit, which is called a coprocessor 1, that is used to execute floating point instructions. So the floating point arithmetic unit, what it does, it reads floating point registers. So the data is stored inside these registers. It executes the instruction, computes the result, and writes back this result into a floating point register. Any register can be read, any register can be written. Finally, we have here the trap and memory unit. Okay, this is used specifically when an exception happens. So when there is an exception like overflow, or we have a different type of an exception, okay, then the CPU is going to interrupt the execution. Or when you have an interrupt, or when you have, let us say, an exception, then this is going to stop the execution of the program. The exception PC, okay, this will contain the address of the instruction that caused the exception, the cause of the exception, the status, and if this exception was caused by a bad address, then the bad address will be stored in a special register here. So this unit is specifically designed to handle exceptions and interrupts. Okay, now all of these units exist on a single chip. Okay, so I'm showing them as different units, okay, from the programmer point of view, but really physically they exist inside the same chip. Now, instructions can address memory. I'm showing here a 32-bit architecture. So the memory consists of 2 to the power 32 bytes. It can be addressed. The memory addresses exist inside the general purpose registers. You can use a register to store a memory address, and you can use it to address memory. You can address the memory as by byte. Okay, so you can load a byte or store a byte inside the memory. You can address it okay, as 2 bytes, we call it a half word, or you can address it as 4 bytes, which is called a word. So the word here means 4 bytes. So you have 2 to the power 32 bytes. Yeah, that's the maximum space that can be addressed in the memory. So the maximum size of the memory in a 32-bit architecture can be 2 to the power 32 bytes. So 2 to the power 32 is 4 gigabytes. And 2 to the power 32 bytes is equal to 2 to the power 30 words, because each word is 4 bytes. That was in the past. Okay, today, 2 to the power 32 bytes, 4 gigabytes might not be sufficient. If you would like to have a larger memory, you have to use more bits for the address. So for this reason, people have switched over the past decade, okay, or even before that, they made a transition from 32-bit to 64-bit. So they increased the size of the registers, okay, from 32-bit to 64-bit, so that they can address more memory and they can increase the size of the main memory. Okay, is this clear? Students, are you with me? Okay. Right. So these are the MIPS general purpose registers that we are going to use them in programming. So they are numbered from register 0 to register 31. The assembler uses a special notation, which is the $sign, to indicate that this is register. Okay, so $0 means register 0. Some assemblers use R0, R1, R2 up to R31. But in the case of the Mars tool that we are going to use in this course and in the lab uses the $notation. to indicate that these are registers. Sorry, these are registers that exist in the hardware. And each register consists of 32 bits. As I said, that register 0 is always 0. It's forced by the hardware. So the hardware forces the value of register 0 to be always 0. And then each register here can actually have a special use, okay, by the software. So the software can use these registers in a special way. For example, register 31, it's used to store the return address. So it's called the return address register, or RA. So we're going to give names to these registers. So for example, register 0, we'll just write it as $0. Register 1 is called the assembler temporary register, or AT. Register 2 and register 3 are used to return values of a function. So when a function would like to return a result back to its caller, is going to place the result in these two registers. So typically, if we need only one result, we place it in V0, but you can return even two results. Okay, a function can return two results in V0 and V1. Okay, a function can receive its arguments in A0, A1, A2, and A3. So these are registers 4 to 7. This is how we write functions in assembly. I'll come back to functions in great detail later. Okay, so after I finish this introduction, I'll talk about many things, including how we write functions in assembly. There are registers that store just temporary values, like register 8 to register 15. These are called T0 to T7. Now, some registers have to be preserved across function calls. We call them saved registers from S0 to S7. There are more temporary registers, okay, 24 and 25. These are called T8, T9. Some registers are reserved by the operating system kernel. We have here the stack pointer, the frame pointer. These are used to implement a stack in memory. And these are just pointers, or they contain memory addresses. Okay, so this is the way that the software defines these registers. So from the hardware perspective, the hardware defines 32 registers from register 0 to register 31. Okay, register 0 is hardwired to 0. It's always 0. The other registers can be used in any way that you want, but the software, okay, to standardizes the use of these registers. Okay. The instruction formats are explained in this slide. All the instructions are 32-bit wide. So the nice thing about the MIPS architecture is that it forces all the instructions to be 32 bits. So each instruction in memory is 32 bits, and there are 3 instruction formats. The R format is what is known as the register format, or the R-type format. It has this format. The upper 6 bits is the opcode. And then we have RS, RT, RD. These are the register fields. We have SA as the shift amount, and we have a 6-bit function. In the case of the immediate format, the I-type format, it has also a 6-bit opcode. It has 2 registers, RS and RT, and a 16-bit immediate. And finally, we have the jump format that has just an opcode and a 26-bit immediate. So now the formats, okay, they differ in terms of the fields. So each format has different fields. Now notice that all the formats have a 6-bit opcode. So what is common in all instructions, okay, is the 6-bit opcode. Now the nice thing about the MIPS architecture, it has all the instructions to be 32 bits in memory. So every instruction is 32 bits in memory. This will simplify their fetching and decoding because they have fixed size. On the other hand, there are architectures like, for example, the Intel architecture that defines the instructions to have a variable size. Now, 32 bits means 4 bytes. So every instruction occupies 4 bytes in memory. And these 32 bits are divided into different fields. Yani, for example, the 6-bit opcode, we have 5 bits for each register field, RS, RT, RD. These are 3 registers. Typically, 2 are used to be read, and 1 is written. So we read here RS is a source register. Now 5 bits for the field, because we can address, with 5 bits, we can address 32 registers. Okay, so 2 to the power 5 is equal to 32. And because we have here a 5-bit field, we can address 32 registers, which are shown in the previous slide. So notice that here that we have 32 registers, so we can specify which 2 registers to read and which register to write using these 5-bit fields. So now we have here 6 plus 5 plus 5, these are 16. Here we have 5 plus 5 plus 6, we have another 16 bits. So in total, we have 32 bits. The immediate type is called actually immediate because it contains a 16-bit immediate. This is just a constant, which is part of the instruction format. I'll talk about these instructions in more detail later. I'll come back to them. And we have the jump. Notice that the jump does not really have any register. It only has a 26-bit constant. This 26-bit constant is used as an address. So this is used by the jump and link instruction. Okay, we have 2 instructions that use this format, and they are specifically used to jump in memory. Okay, so these are the formats of the instructions, how they appear in binary, how the instructions are implemented in binary or are defined in binary by the architecture. Let me introduce now assembly language. Okay, so what is assembly language? It's a low-level programming language for a computer system. So we have seen in the introduction, okay, Dr. Tabbakh introduced the difference between assembly language, high-level language, and machine language. Do you remember that? Okay, from the introduction last?
Yes.
Okay, so when a programmer writes a program in a high-level programming language, let us say he's writing it in C or Java or whatever programming language the programmer is using. Now, this language does not really depend on how the architecture of the processor is defined. It does not really depend. It's machine independent. Okay, so when you are writing a program, let us say in C, in the C programming language, you can write the program in C, and you can actually have the program translated to the Intel architecture or to the MIPS architecture or to the ARM architecture. So the program itself is not related to the processor, how the processor is defined, the architecture is defined. On the other hand, when you write a program in assembly language, we call this low-level programming because you are using the machine instructions. So there is a one-to-one correspondence between assembly language and the machine instructions. The difference between assembly language and machine language, can you tell me what's the difference between these two? Assembly language and machine language.
The machine language is a binary, one and zeros.
Yes.
And the assembly language is a translation for that, so that human can understand.
Yes, it's actually is a readable format of the machine instructions. So basically, if you have an add instruction, you write it as add, as text. So when you are writing the instruction in assembly, you write the instruction, for example, add, and you can say add register 1 plus register 2 and put the result in register 3. Okay, so you type it as text. So when you type it as text, okay, you make the instruction readable. On the other hand, the machine language, it's just binary, ones and zeros. So there is a translator that will translate the assembly language program into machine language. And this translator is called the assembler. So the assembler here is going to convert. Let me use my highlighter. So the assembler is just a program. It's a translator. It translates a program which is written in assembly language into machine language or machine code. Sorry. Notice that the translation is very simple. When you are writing a program in assembly, there is a one-to-one correspondence, okay, between the assembly language and the machine instructions. So the assembler knows that the add instruction is going to be translated using one of these formats that we have seen in the previous slide. Remember, these actually are the instruction formats. These are the machine instructions. Okay, this is their formats in binary. So the opcode will be defined as ones and zeros. RS, RT, RD, these will be defined in binary. So basically the instruction will be in binary, and each instruction will be 32 bits, and the instructions will be stored in memory. So the entire program will be stored in memory, and the CPU is going to fetch these instructions one by one and is going to execute them. Okay. Now, why people? The assembly language uses. So we have, when you write a program in assembly, okay, we write it as text. So we use mnemonics. So mnemonics are what? This is just text. These are the names of the low-level machine instructions. Yani, for example, I can say add, subtract. I will write it as SUB, subtract, or multiply, or shift left logical, SLL, for example, or load, or store. Okay, so we use these names of the low-level machine instructions, and when we are typing the instructions, okay, in assembly, we use labels. Labels, we use them, for example, when I would like to jump, or I would like to branch, or I would like to give names of variables, okay, in memory. So I would like to have variables in memory, and I would like to assign to them names. So these are the labels. We use directives. Now these directives, okay, are like commands to the assembler. Of course, these are not machine instructions, but we use them to define data or define constants. Okay, these are called directives, or to indicate the beginning of a code segment or the beginning of a data segment in memory. And we write macros. Macros are defined by the assembler, depending, of course, on the assembler that you are using, okay, to facilitate, okay, and the inline expansion of text into other codes. So this will simplify writing the code in assembly. Okay, so there are three types of statements in assembly language. We have the executable instructions. Now, these instructions, we write them in assembly, but we know that these instructions are going to generate code or machine instructions, and they are going to be executed by the processor at runtime. So we call them executable, because the processor or the CPU is going to execute these instructions. We have pseudo instructions and macros. This is a different type of a statement that you can write in assembly. But these pseudo instructions and macros, it is just a facility which is defined by the assembler to introduce the new instructions that do not exist in the hardware. So these are not really real instructions, but what the assembler is going to do is going to expand the pseudo instruction or the macro into a sequence of instructions. So when you define pseudo instructions or macros inside the assembler, you are telling the assembler every time you encounter the name of this pseudo instruction or the name of this macro, expanded, okay, inside the code. So we call this inline expansion of the pseudo instruction or the macro inside the code, inside the assembly language. Okay, so these are translated by the assembler into real instructions. Okay, again, they are executable because the assembler is going to translate them into real instructions. And the purpose why we have them is to simplify the task of the programmer. So the assembler is providing some kind of a facility to the programmer to simplify his task. And we have the third type of statement here, which are the directives. So these directives are defined by the assembler, and they provide information to the assembler while translating the program. So for example, you can specify, we can actually use these directives to allocate memory for variables, to define the segments in memory. So these directives are non-executable. Okay, so they are not really executed by the processor. And they are not really part of the instruction set. So they are defined only by the assembler. Now, the assembler is just a translator, is just a program, and different assemblers can have different syntaxes, different directives. But really, the concept is the same, okay? Although they might slightly differ, okay, from one assembler to another assembler. But the concept of directives, pseudo instructions, macros, okay, these are essentially the same, okay, even though the syntax can differ from one assembler to another. So assembly language is a simpler language than the high-level programming languages, okay, which are used by programmers, but these are needed. In the past, before people have invented high-level programming languages, people used only assembly. Yani, if we go back to the 1950s and 1960s, people use a lot of assembly language, okay, to write programs. But then with the introduction of high-level programming languages back in the 1950s and 1960s, people used assembly language to write compilers. So the difference between the assembler and the compiler is that the assembler is just a simple translator. The compiler is a much more complex translator, because the compiler, what it does, it translates from high-level, okay, programming language to assembly language. And there is no one-to-one correspondence between high-level and assembly. However, the assembler is very simple because there is a one-to-one correspondence between assembly and machine language. Is this clear? Do you have any questions?
Yes.
Okay. Right, so let us take a look now at some details. Okay, let us take a look here at the instructions. The way that the syntax of the instruction is defined in assembly language, the instruction starts with a label. Now notice that the label here is optional. I'm using the square brackets here to indicate that this is an optional label. Not every instruction has to have a label. You can actually write an instruction without any label. The mnemonic here is the name of the instruction. And then you can actually have here different number of operands. Some instructions have 0 operands. Some of them have 1, 2, or 3, okay, depending on the instruction. And finally, here we have a comment. Okay, so the comment, the comment is just introduced, okay, to explain the purpose of this instruction, okay, and it's optional. Okay, so the programmer may or may not really write a comment. So the label here marks the address of the instruction in memory, and it has to use a colon if you write a label. The mnemonic identifies the operation, like for example, add, subtract. This is what we call the mnemonic. The operands can be like registers, like for example here, T0, T0, 1. These are the operands. So here's an example. L1 here is the label. Notice that the label here, you can give it any name, but it has to end with a colon. That's actually the syntax of a label. Add IU, add immediate, unsigned. That's actually add IU. This is the mnemonic. And then we have here T0, T0, 1. These are 3 operands. So what we would like to do is that I would like to add register T0 plus 1 and store the result in T0. So T0 is a temporary register. Okay, if we just go back here, okay, to the list of registers, T0 is nothing but register number 8 in the hardware. So register number 8 in the hardware is T0. Okay, so what I would like to do in this instruction, I would like to increment the value of register T0. So I'm going to add T0 plus 1 and place the result in T0. That's what this instruction does. It will increment the value of T0 and place the result back into the same register T0. You could have written the result into a different register. And notice that one here is an immediate. So this instruction is of the immediate type. And if I would like to go back to the format, it uses the immediate format. And the one here is the immediate constant. Okay. So that actually is the immediate type because we are using one. One is a constant. It's an immediate. So immediate means a constant that you would like to have inside the instruction. Now, comments, these are just like you write comments in a high-level programming language. You can write comments in assembly language. So assembly is just like a programming language, but it is like a low-level programming language. People invented assembly language long before inventing high-level programming language. Okay, so you can just write a comment. You can actually have a single line comment. This will begin with the hash symbol and it will terminate at the end of the line. This is what we call a comment. The comment itself is optional, but it's very important at the same time because you can actually explain, you can write comments at the beginning of the program, explaining the purpose of the program. You can write who is the author, okay, if it was revised, the dates, all of this. You can indicate the input and the output. You can write comments at the beginning of each function or procedure that you have inside your program. You can explain, let us say, a sequence of instructions or the algorithm that you are using. So people write comments, and comments become more important when you are programming in assembly language because it's really harder to understand assembly than understanding a high-level programming language. So high-level programming languages were designed to be easier, okay, to use than the assembly language. But assembly language is essential because eventually all the programs have to be translated to assembly and then machine language so that they can be executed by the processor. Okay, so comments are very important when you are programming in assembly. You can indicate, for example, if you are using specific registers, okay, what's the need? Why are you using these registers? For what purpose? You can explain all of these things with comments. Here's an example of a program template. Okay, notice that all of these are comments at the beginning, like the title, the file name, the author, the date, description, input, output. You can indicate the beginning of a data segment. Notice that .data is a directive. Okay, it's a directive. .text is a directive. .global is another directive. So .text means the beginning of the code segment. So this is where we write the instructions. .data indicates the beginning of the data segment. So this is where we define our data. I'm writing here 3 dots, but of course we have to fill this. Okay, we have to define data in the data segment. You can define data, you can define strings, constants, whatever you want inside the program. .text, this is the beginning of the code segment. You can write one function like the main function, or you can actually have many functions in your program. So main here, I'm defining main as a global. Okay, as global.global here. Notice that there is no A. For some reason, okay, the programmer, okay, the one who wrote these defined the assembler did not really want to have an A here, although, yeah, just to make it actually just shorter directive. Anyways, it indicates that main here is a global symbol, okay, and this is important when you have the program. Sometimes you write a program into separate files and then you have to link them. Okay, so it makes a function. If a function you would like to make it visible in other files, you have to define it as a global. So here we are defining main. This is the program entry, and you can write all the instructions. And then at the end, you would like to exit the program. You can use a system call to exit, and this is system call number 10. I'll talk about system calls in great detail later. Okay, so that's just an example about how you write a program in assembly. Mostly it's written as comments, but of course you have to fill it with instructions and you have to define the data in the data segment. So it's really quite simple, okay? Assembly language is quite simple, but at the same time, it's really difficult to write and to read. But the syntax is really simple. So we have seen here some directives. These are not the only directives. So according to the assembler can define a number of directives. For example, .data, we have seen in the previous slide, .data. This is a directive. So anything that starts with a dot, okay, this is the syntax. Dot means a directive. So .data is a directive that will define the data segment. So it indicates that this is the starting point of the data segment. This is where you define your data, the data that will be used by the program. .text, text here means code, okay, or instructions. So you are defining the code segment. Okay, that's the meaning of .text. So this is where you are defining the program. This is basically where you write the program instructions. Okay, so you write them under the .text. Okay, so this is the code segment. And we have seen .global. This is a third directive. You are declaring a symbol or a label. So I mean here by symbol as a label, as a global. Okay, so in the previous slide, we have seen that main here is my label. Okay, now that's actually is a global symbol. Okay, so it means that you are making, okay, this symbol visible and it can be referenced from other files. Because a program, typically in this course, we just write the program as a single file because these programs are really small and the exercises and the problems that we have in this course are really small. But in reality, software can be huge. And you can actually have program written in hundreds, if not really thousands of files. Okay. So in this case, you would like to have certain symbols referenced by, okay, let us say different functions that exist in other files. So you have to make them global. That's the meaning of the global directive. So you might actually have a function that exists in one file and you have another function in a different file that you would like to call it. Okay, so one function calling another function, but they don't exist in the same file. So we need actually certain directives to indicate, okay, the visibility, if you would like, of these functions or these symbols, okay, across different files. Okay, questions about this? Right. This is the layout of a program in memory. Okay, so you can see that each program is divided into a number of segments. So we have the text segment. So what I mean here by text, it means the code segment. So the machine instructions will be in this segment, starting at a specific address. So when the assembler translates a program, it places the machine instructions in the text segment. So these instructions will be fetched and executed by the processor at runtime. It places the data in the data segment. There are two types of data. We have static data, which is defined by the assembler. So when the programmer actually defines the data under the .data directive, these are static data. So static means that the data will exist from the beginning of the execution of the program until you terminate the execution of the program. So we have a static area. This area does not really change at runtime. And we have the dynamic area, which is called the heap. Okay, many high-level programming languages today, almost all of them, all modern high-level programming languages, what they do is that they allocate memory dynamically at runtime. So this is so the variables that you are allocating at runtime will exist in a certain area in the data segment, and this area is dynamic. So it can actually increase and decrease dynamically at runtime, and it's well known as the heap. Now, I will show you later how we can use a system call to allocate memory at runtime. So you can allocate a variable dynamically. So the variable did not exist. And while you are executing the program, you allocate the variable. It will exist in memory. And you can see that this dynamic area or the heap can increase at runtime. So basically, there is a gap here between the data segment. On top, we have the stack segment. So there is a gap here, and this gap can be used to allocate memory at runtime. So you can request more memory from the system, and this dynamic area or the heap can grow at runtime. there is a stack segment that appears on top. This stack segment is also allowed to grow, but it's going to grow here, okay, downwards. Okay, so you can see it's going downwards. So therefore, the stack segment appears, okay, on top, okay, of memory according to this layout, and is going to grow downwards toward the lower memory addresses. So the heap is going to grow upwards, whereas the stack is going to grow downwards. Now, the stack segment is very important for implementing functions, okay, for saving registers, for allocating data for functions. Okay, so we allocate them in the stack segment. Any question about this?
Yes, Doctor.
Fadal, and the question?
When we will get a stack overflow exception here, is it
well,
when
stack
the dynamic
overflow means that you have used all the maximum space that was allocated for a given stack. So typically there are limits in memory because memory itself is finite. If you keep allocating space in the stack segment, you will get stack overflow. Okay, so that's an exception indicating that you have reached the limit, okay, that was set, let us say, by the operating system. So the operating system can place limits on the maximum size of a stack segment. And if you reach this limit, you will get stack overflow. You can also have heap overflow if you allocate too much memory, and therefore you reach the limit that was set by the operating system. So typically the operating system manages the memory, okay, and you can make a system call to allocate space on the heap. But if you have allocated the maximum space that was, you reach the limit, okay, then in this case you will get actually a heap overflow. So you have different types of overflow. We have stack overflow and we have heap overflow. So the stack and the heap, both of them are dynamic, okay, both of them are dynamic. But the stack is mainly used by functions. We'll see how the stack is used by functions, okay, in later lectures. The heap is used, let us say, to allocate dynamic variables. So the program, for example, when it uses the new operator in high-level programming languages, the new is going to allocate space on the heap. Many high-level programming languages, okay, allocate variables dynamically on the heap at runtime as the program is running. Is this clear?
Yeah, it is clear.
So this is just like the image, okay, or the layout of the program in memory. Now on top, okay, above the stack segment, which is not really shown, there is the operating system itself, but I'm not showing it. You might also have libraries and other things. So this image is very simple. In fact, today in a modern system is a lot more complex than this. Well, next I'm going to show you how we allocate data in this static area of the data segment. Later I'll come back and show you how we can allocate data dynamically in the heap. And when I talk about functions, I'll talk about the stack segment. So I will come back to these. Okay. As I said before, okay, feel free to interrupt me if you have any question. So I'm going to move now. Okay, so the instructions appear in the text segment. And the static data appears in the static area of the data segment. So let me show you how we define data in assembly language. Okay, so this data will be static data. So this is the data definition statement. Okay, this is the syntax in assembly. So the syntax is defined by the assembler. So the assembler defines a language, which is, we call it the assembly language. So when you are programming in assembly, you have to use the syntax of the assembly language. So you start with a name. The name here is optional. You can see here, I'm just enclosing it between square brackets. So that's the name or the label. So this name here will correspond to the address of the data in memory. And then you use a directive. So this directive is used to allocate data in the static area of the data segment. For example, you can use .word. Here the name can be, for example, var1. You have to write a column. Okay, so this is part of the syntax. And then notice the directive always starts with a dot word. That's how it's defined by the assembler. And then you can have one or more initializers. So in this example, I only have one initializer, which is 10. So this var1 is a word. Word means 4 bytes. So the assembler is going to allocate 4 bytes for this variable and it's going to initialize this 4 bytes with the number 10. So it is just an integer. Now you can actually have multiple initializers. You can actually have an array, if you would like, of initializers, and you can initialize multiple words in memory. You can separate them by a comma, and you can actually have multiple of these. Now, when the assembler initializes 10 in memory, all the data becomes in binary. So this 10 here, which is in decimal, is going to be translated to binary. So whether the number is positive or negative, it was negative, it will be in the 2's complement representation. So when we initialize memory, of course, the data in memory will be in binary. But when you define data in assembly language, you can use binary, you can use decimal, you can use octal or hexadecimal, you can use different number systems. Okay, so the assembler allows you to define data, okay, in different number systems. This is just decimal. So there are different data directives. In this example, I showed .word. It means that the data itself, okay, will be 4 bytes in memory. But there are other directives. For example, you have .byte. It means that the data will be just a single byte in memory. You cannot really have less than 1 byte. So when you allocate data in memory, it will be in bytes or multiple of bytes. So .byte means just a single byte. Single byte means 8 bits in memory. .half, it means half word, which means 2 bytes or 16 bits. So each value will be 16 bits. It will allocate 16 bits in memory for each half word. .word means 4 bytes or 32 bits. That's .word that we have seen in the previous example. We have .float and .double. These are for floating point numbers. Okay, numbers that have a fraction and an exponent. I'll talk about these in great detail later. So these are floating point numbers. .float means 4 bytes is allocated for each floating point number. And .double means that we are allocating 8 bytes for each floating point number. For example, you can have the number, let us say 1.2, or let us say minus 5.3 times 10 to the power, let us say 15. Okay, you can actually have very large numbers as floating point numbers, or you can use negative exponents to indicate that the number actually is a fraction. Okay, let us say minus 5.3 times 10 to the power, let us say minus 5. So I'll talk about these floating point numbers in a great detail. So the difference between .float and .double is the size of the data, whether the size is 4 bytes or 8 bytes. In addition, you can have .ASCII and .ASCII-Z. These are used for strings. So if you would like to allocate memory for a string, use the .ASCII or the .ASCII-Z. The difference between these two is that is going to .ASCII-Z is going to insert a null byte, a null character at the end of the string. Now, ASCII means that you are going to allocate a sequence of bytes. So each character in the string will be a byte in memory, and therefore is going to allocate a sequence of bytes for the string. So the string here is encoded in ASCII. You can just type the string and enclose it between double quotes, but the assembler is going to convert each character in the string to its binary representation according to the character code for that, according to the coding of the character in the ASCII character set. Okay, so that's the meaning. .ASCII-Z is very similar to .ASCII, but as I said, it's going to insert one extra character at the end of the string. This is not shown in the string. So to terminate the string with a null character. So some programming languages, like the C programming language, okay, it terminates every string with a null character. So every time you have a string, it has to be terminated with a null character. So it uses the .ASCII Z. Other programming languages might not terminate the string with a null character. It might use another field to specify the length of the string. It uses other information about the string, which is the length. For example, the C programming language uses a null character. So in many examples, I'm going to show you the .ASCII Z because we would like to insert a null character at the end of the string. There is also the .space directive. .space is going to initialize n bytes in memory, but these n bytes will be uninitialized. So if you just would like to allocate space without initializing it, use the .space directive. You can, let us say you would like to allocate 100 bytes, 1000 bytes, whatever number of bytes that you need to allocate in your program. Okay? Yes, Mushtaba, you have a question?
.ASCII, can we use non-English characters? Because non-English characters in ASCII
well, this is
okay.
.ASCII here, we are allocating single bytes. We're not really using it for Unicode. Of course, today modern assemblers actually can support this, but we are using with a very simple assembler here, which is comes with the Mars tool. So we are going to limit this only to ASCII characters. Okay, so we're not going to use the extended, or we're not going to use Unicode. Okay, that allows us to use a variety of characters or letters from different natural languages. Yani, we're not going to mix English with Arabic or with, let us say, with other
okay. Thank you.
natural languages. But this is possible. Okay, this is possible. But .ASCII, it limits each character to a single byte. Yani, you cannot use like Chinese or Korean or something like this. Okay. We can actually have strings that allow you to use multiple bytes per character, and these will allow you, okay, to use character codes for other natural languages. There is nothing that prevents us from doing this. But .ASCII is limited, okay? .ASCII and .ASCII Z are limited to a single byte per character, and therefore they limit this to the ASCII set, ASCII character set only. Any other question? Okay, so these are the directives that you can use. I have many examples here. Now notice that first you have to start with .data as a directive that marks the beginning of the data segment. And all of this data is static, as I said, it's not dynamic. So the programmer has specified var1, var2, all of these are labels, okay, for static data. I have here str1 for a string, str2, I have array, which is .space. So let us take a look at them one by one. So .byte here means that every value here, okay, will be a single byte in memory. So I have 5 initializers. Okay, so these are called initializers, just constant values. You can have, for example, a character, which is enclosed between single quotes. This is a character. It's a single byte. So when you write a character between single quotes, like capital A, the assembler knows what is the code. It's a binary value. So, for example, capital A will be 41 in hexadecimal. It's going to convert it to a single byte in binary, and it's going to initialize, okay, memory with this, with the binary code of character A. Here I have character E. Here I have the number 127. So everything will be in binary, regardless whether you write it as a character or you write it in decimal like 127 or a -1. -1 will be a single byte. All the bits will be all ones. That's actually -1 in the 2's complement representation. So you can also have negative numbers, okay? \n, notice that I'm using the C escape sequence. It's the same escape sequence which is used in many different programming languages. Java also uses the same escape sequence that it took from C. Okay, so what this means that this is a new line character. It's a control character. It's not a printable character. If you print it, it will just advance the cursor to the beginning of next line. So this is known as the new line character, and it has an ASCII code. Okay, so it will be also appears in binary. So in binary, everything is in bits, right? So the computer, the hardware, does not really know, okay, what are these? Are these characters, integers, control characters? It does not really know what are these. It's the software that gives meaning, okay, to these characters, or to these, bytes or bits. So the bits have no meaning, the bytes have no meaning. It's the software, okay, which is giving a meaning to these bits and bytes in memory. So the smallest entity that you can allocate is a byte, and each byte consists of 8 bits. You can have .have. It means that each initializer here, each value, will be 2 bytes in memory. So if a single byte is not sufficient, then you have to use 2 bytes. For example, here, -10. Here I'm showing it 0x means that this number is in hexadecimal. This is the notation of a hexadecimal number. Okay, F. Now notice that each F will be 4 bits in binary, and we have four of these. So this is a 16-bit value. This is why I'm using it .have. 16 means that 16 bits means that it's 2 bytes in memory. The next one is interesting. It's .word. I'm showing it also in hexadecimal. Each digit is 4 bits. I have 8 digits here. Okay, so 8 times 4 bits, this will be 32 bits. So this number is a 32-bit number. 32 bits, if you divide it by 8, it will be 4 bytes. 4 bytes means .word. Okay, that's actually here is a 4-byte number. And notice that I'm using colon 100. This is a syntax in the assembly language indicating that you would like to replicate the same number 100 times. In other words, var3 will be an array of 100 words, and each word is initialized with the same value. So you'll see the same value replicated 100 times in the data segment. I have var4, which is .float, so 12.3 -0.1. These are floating point numbers. var5 will be also a floating point number. Yes, Khalid. Yes, Khalid.
Doctor, what does the 0x mean?
0x means that if you start a number with 0x, it means that this number is represented in hexadecimal. It exists in high-level programming languages, like, for example, in C and Java. They use exactly the same notation, okay, to indicate that this number is not decimal, it is hexadecimal. Okay, that's the meaning of 0x. There is also 0b for binary. If you would like to have, let us say, a number in binary, you start with 0b, but you are allowed to use only the digits 0 and 1. You cannot use any other digit. In the case of hexadecimal, you can actually use the digits from 0 to 9 and A to F, because A to F will be digits in hexadecimal. Is this clear?
Yes, Doctor, thank you.
Okay, good. Right. So here .float and .double, these are floating point numbers. The difference is that .float, each initializer, each value here, will be represented as 4 bytes in memory, whereas .double will use 8 bytes for a single value. Now notice that I'm writing it as 1.5 e minus 10. So e here means the exponent is minus 10. It means it's multiplied by 10. The base is 10, and the exponent is -10. So this is like a very tiny fraction, okay? And we are expressing it using the scientific notation. And this is how you write it in, okay? This is the syntax of the number, how it appears in assembly. You can write exactly the same thing in a high-level programming language. By the way, the numbers, how they appear in assembly, exactly the same way. So these are just constants, okay, that you are assigning to these variables. Notice that .ASCII, Z, these are strings, okay? So they have to be enclosed between double quotes. Each character is a byte in memory. So capital A will be a byte, the space will be a byte, S will be a byte, and so on. \n, these are not 2 bytes. This is just a single byte. So \n is the new line character. It starts with backslash. So when something starts with backslash, it means that you have to look at it as a sequence. So the sequence \n, okay, is known as the new line character. It's going to occupy 1 byte in memory, not 2 bytes. There are many escape sequences that you can use. If you would like to have backslash itself, you have to write it \\\. Okay. If you would like to have the code inside the string, you write it \single quote or \double quotes. So you can use it for certain sequences. If you would like to have a tab, the tab cannot be printed, but you can write it as \t. So there are a number of control characters or special characters that you have to use them with backslash. Okay, so notice that part of the syntax of the string is the double quote. So you cannot write it inside the string because it will terminate the string. So if you would like to have double quotes inside the string, you have to write it as \double quotes. Okay. Here I have str2. This is also a string, but this string is terminated with the null character. So I'm calling it null terminated string. There is one extra character which is not really shown at the end of the string, which is the null char. So automatically the assembler, when it sees the end of the string, which is this double quotes, is going to insert a null character to mark the end of the string. Finally, we have here array.space 100. It means that we are going to allocate 100 bytes for this array. So that's the space that we're allocating. So it's in bytes, but without initializing it. So if you want to allocate space without initializing it, use the .space directive. Okay, so notice here the syntax .100, sorry, colon 100. So we use this, let me just highlight it here. So the colon 100 has special meaning. So that indicates, if you use the colon followed by a number here, indicates that this value has to be replicated 100 times. So we have an array of 100 words, what's dot word here? 100 words which are all initialized with the same value, okay? And the value is shown here in hexadecimal. Any question about this? Clear?
Yes, Doctor. I have a question.
Yes, tell me.
The array, the directive.space is of what type? A string?
Well, you see the difference between assembly language and between high-level programming languages is high-level programming languages are typed languages. You specify the type of a variable. In the case of assembly language, it's untyped. So when I say .space, there is no type associated with this space. You can use the array as an array of bytes. Yani, for example, you can use it to store a string that has a maximum length of 100 bytes. So you are limiting the length of the string to 100 bytes. I can use it to store an array of, let us say, integers, and each integer can be a word, 4 bytes, but therefore I can use these 100 bytes to store only 25 integers. So the same space can be used actually for different types. That's the interesting thing about assembly, is that there is no typing system associated with assembly. It's all up to you. You would like to use these bytes in memory for whatever purpose. So there is no restriction, okay, in assembly language. You can use whatever type in this space, okay?
Okay, I have another question. Can I?
Oh.
What happens if I, for example, I initialize the value that is, if I write the .byte and the value, for example, was 128, bigger than a byte? What error?
Well, 128 can fit in a single byte, okay?
Maybe
so
larger value.
if you look at the byte as unsigned, 128 can fit, but if you write 256, it cannot fit in a single byte. Okay, so if you look at 108 as a signed number, it becomes negative 128. Okay, if you look at my -1 as unsigned, it becomes 255. So you can give different meanings different meanings for these bits or these bytes that exist in memory. But if you write a number here, which is larger than the maximum value that you can store in a single byte, if this is the question, okay, one of two things can happen. Okay, if the assembler is smart, it can actually catch this as an error and report to you that this is a syntax error. Because if you, for example, you write the number 1000 here, 1000 cannot really fit in a single byte. Okay, so that would be one possibility. Another possibility, okay, I did not check this, but you can actually check it, okay, with the Mars tool. Either the Mars tool is going to report this as an error, okay, and tell you that the value is larger. It cannot really fit in a single byte. There is a second possibility, depending, of course, on how the assembler was written by the programmer. Okay, if the programmer did not really catch this error, okay, so the number 1000, it fits in 2 bytes, it might just look at the least significant byte and ignore the rest. So therefore, a different value will be stored in a byte inside memory. Yani, you might actually get a different value. So if the number 1000 cannot really fit in a single byte, then it will, if the assembler is silent, it might put just the least significant byte and ignore the upper bits. So the number, if it exceeds more than 8 bits, it will take only the least significant 8 bits and will store them in memory, ignoring the upper bits. Sometimes some assemblers actually will remain silent, depending, of course, on how the assembler. So it will leave it to the programmer. Okay. If you write something like here, a very large value, I'm not going to take the entire value. I'm going just to take the least significant 8 bits and store it as a byte in memory. So it's your responsibility to ensure that your program is correct. Of course, if you are writing this in a high-level programming language, the compiler will catch these errors. Okay. So some assemblers actually might catch the error. Some assemblers might remain silent. It depends, of course, on the assembler. Okay.
Okay. Thank you very much.
Right. So these are just examples of data definition statements. Notice that the last example here, array.space100, it means 100 bytes which are not initialized. Next, I need to talk about 2 important concepts about memory. Okay, so memory alignment and byte ordering. Now, memory alignment is very important when you are dealing with data which is larger than a single byte. For example, if you are dealing with words, half words, or double words. So each value requires more than 1 byte in memory. Alignment becomes important. So let me talk about memory alignment first. So memory alignment, okay, well, first memory, when you look at memory, memory is just, you can view it as an array of bytes. And each byte has an address in memory. So we call it that the memory is addressable. You provide the address of a given byte in memory, then you can read or you can write the byte in memory. That's memory, okay? So in any computer system, you have memory, and the memory itself consists of bytes, and you can address the bytes in memory, okay? So the smallest entity that you can address is the byte in memory. You cannot address the individual bits, but you can address the byte, and each byte is 8 bits. But sometimes the data is larger than a single byte. Okay, so you can start here at address 0. This is 1 byte, and address 1, 2, 3. Then you here jump to address 4, 5, 6, 7. Then you go to address 8, and so on. So these are memory addresses here, which are shown to the left. And these are bytes in memory. But I'm showing that here in each row, I'm showing like 4 bytes from 0 to 3. Here I have from 4 to 7. Here I have from 8 to 11, and so on. Okay? Right. Now, what if I would like to have a word in memory? If I would like to have a word, the word consists of 4 bytes. For example, an instruction would have 4 bytes in memory. Each instruction, we have seen that before, that each instruction, when we look at the instruction formats in my last lecture, we have seen that each instruction is 32 bits. Okay, so all the instructions in MIPS, each instruction is 32 bits. So 32 bits means 4 bytes. You need 4 bytes per instruction. If you have an integer, okay, each integer will be, for example, the type int in Java or in the C programming language, okay, is 4 bytes. So when you are dealing with integers, you are dealing with, so each integer value occupies more than 1 byte. It needs 4 bytes per integer. So now what's important is that if you have something which is larger than a byte, like a word, you need 4 bytes. Okay, so you need to allocate 4 consecutive bytes in memory. Now, the meaning of alignment is that you look at the address of the word in memory. Now, the word is 4 bytes. So when you say the address of the word, it means that the address of the first byte in this word, because the word consists of 4 consecutive bytes. Now, if the address is multiple of 4, then we say, because the word is 4 bytes. Okay, so if the address is multiple of the size of the entity that you would like to allocate, okay, so for example, in the case of the word is 4 bytes, so the address should be multiple of 4 bytes. Then we say that the data is aligned in memory. And if it is not multiple of 4, then in this case, we say that the data is not aligned in memory. Okay, that's very simple. So for memory alignment, the address must be a multiple of the size of the data. So if the data is 4 bytes, then therefore the address must be multiple of its size. That's it, multiple of 4. If you are dealing, let us say, with double words, okay, that's the case, for example, for double, okay, double precision floating point numbers. I'll talk about these later. The data is 8 bytes. It's not only 4 bytes, it's actually 8 bytes. So my data, the size of my data is 8 bytes. And therefore, we need to have the address multiple of 8, not multiple of 4. If you are dealing with a string, ASCII characters, each character is just a single byte, 1 byte. So therefore, there is no alignment for bytes. The byte, you can place it anywhere in memory. If you are dealing with half words, okay, half word means that the data size is 2 bytes. So therefore, the address must be multiple of 2 because the size is 2. So therefore, the address must be multiple of 2. So multiple of 2, it means that the address is even. Okay, it cannot be odd. That's what it means. So we look at the address. Okay, the address. Now notice that here, let us take a look at this word. The word consists of 4 consecutive bytes. So it starts at address 1, then we have 2, then we have 3, then we have 4. Now, because it starts at 1, not at 0, this word is not aligned. Okay, notice that the word is not aligned. We have 3 bytes here, and I have 1 more byte here. So these are 4 bytes, and they are not aligned. Notice that this word here, again, it occupies 4 bytes. The first one started at address 6, then 7, then 8, then 9. So these are 4 bytes, and these are not aligned. Okay, can you see that? Not aligned. Also, this word starts here at address 11, then 12, 13, 14. It's also not aligned. Whereas this word, which is shown in green on top, okay, it starts at address 16. 16 is divisible by 4, so it's multiple of 4. Okay, then we say that the word is aligned in memory. So notice that 0, 4, 8, 12, these are actually multiple of 4. So if the word starts at these addresses, we say that the address is multiple of 4, then the word will be aligned. Otherwise, if it starts at an address which is not multiple of 4, then the data is not aligned in memory. As simple as that. Okay. Now there's a directive. Yes.
Can you repeat it? I mean, I didn't
I'm
get
going
it.
to show you some examples. Yes. So remember that each word, okay, is 4 bytes in memory, and to have the word to be aligned, its address must be multiple of its size. It must be multiple of 4. So to have the address multiple of 4, for example, 0, 4, 8, 12, and so on, okay, these are multiple of 4, whereas 1, 2, 3 is not multiple of 4. If you have 5, 6, 7, this is not multiple of 4. If you have 9, 10, 11, this is not multiple of 4. So the starting address of the word in memory should be multiple of 4. This is the meaning of alignment. This is for a word because the word is 4 bytes. Now you can use the .align n directive to force alignment. Okay, when I use .align n, it means that the address should be multiple of 2 to the power n. Okay, so it should be multiple here of 2 to the power n. It forces the address of the next data definition to be multiple of 2 to the power n. I'm going to show you some examples to clarify all of this, okay? But before this, I need to talk about another concept. So I'll come back to alignment, but I need to talk about byte ordering. Another important concept, which is related to memory, is the ordering of the bytes within a single word. As I said, if you have an integer, okay, the integer will be a word in memory. It will be 4 bytes, not just 1 byte, it's 4 bytes. So therefore, the question is, in what order these bytes appear in memory? Well, we have 2 ways to order the bytes. We have the little endian byte ordering. Okay, now here what I mean by endian, it is the end. Okay, so when I say little endian, it means that byte 0 starts at address A. Okay, so the least significant byte will appear at the address A. Then byte 1 will be at address A plus 1. Then byte 2 will be at address A plus 2. And byte 3 will be at address A plus 3. But the most important thing is that the least significant byte, this is why I call it little. Little, it means the least significant byte. So the least significant byte, which is at address A, okay, so that's the least, so the address of the word is A. That's the address, and the word consists of 4 bytes. So the first byte is the least significant byte. Okay, so the byte that appears at address A is the least significant byte. So when I would like to transfer this word from memory, this is my memory here, to a register, the register will consist of 32 bits. So 32 bits here means 4 bytes. I'm going to transfer, okay, the byte at address A into the least significant byte. Okay, so notice that I'm going to transfer this to the least significant byte. So maybe I can use here a pen. Okay, so this byte 0 will be transferred here. Is this clear? That's actually is byte 0. That starts at address A. That's the address of byte 0. It will be transferred into the least significant byte. Okay, and then we have byte 1, byte 2, byte 3. So they will be transferred from the least significant byte to the most significant byte. So we call this the little endian byte ordering. On the other hand, we can have a different way to order the bytes. We can have the big endian byte ordering. So what I mean here by big is that the address of the word, the address here is A, it will be the address of the most significant byte. And this most significant byte, you see that when I transfer here the first byte at address A, it becomes the most significant byte inside the register. So we take the first byte at address A, and this is byte 3. It's the most significant byte. Then we have byte 2. Then we have byte 1, byte 0. So we load the register from the most significant byte to the least significant byte. Okay. So notice that here we are going to fill the register from the most significant byte to the least significant byte in this order. Whereas here, in the case of the little endian byte ordering, we fill the bytes from the least significant byte to the most significant byte. So this is a different ordering of the bytes. So the bytes appear slightly differently in memory. So here we start at address A. This is byte 0. We start at the least significant byte, and then we start filling them from the least significant byte to the most significant byte. Whereas in the case of the big endian, we start at byte 3 at address A. So we start at the most significant byte. So we start by filling the most significant byte, and then we can go all the way to the least significant byte. So these are two ways of ordering the bytes within a single word, within a single integer. Okay. So if you would like to see the bytes in memory, how they appear, they can appear in these two different ways. Now, the way that the Intel architecture works is that the Intel architecture uses, okay, the little endian byte ordering. So the Intel architecture uses the little endian byte ordering. So that's one way. So there is no agreement about different processor manufacturers, okay, different architectures, how to do the ordering. People have thought about these two different ways, okay, over the past, let us say, 4 decades. And they came up with these two different strategies. So some use the little endian byte ordering, and some use the big endian. So, for example, the Spark architecture used the big endian. MIPS has an ability to operate in both byte orderings. Okay. Now, because we are using here a simulator for the MIPS architecture, under the Intel architecture, you will find out that if you look very closely into the bytes, you will find that they are according to the little endian byte. So the Mars tool uses the little endian byte ordering to order the bytes within a word. So this is the meaning of byte ordering. Okay. So I need to finish this topic here. Okay, and let me talk about the symbol table. So now I'm going to show you, okay, how the bytes, okay, and their memory addresses, okay, will appear. Now, when the assembler, okay, so the assembler is just a translator. Okay, when it sees a data segment, it's going to allocate, okay, these variables and their values in memory. So it's going to construct a symbol table. Now, the symbol table is going to so the assembler is going to compute the addresses of these labels. So for each label, there is a memory address. And this mapping between the labels and the memory addresses is placed in a table. This table is known as the symbol table. In the lab, for example, in the Mars tool, you can actually see the symbol table. Okay, they are also called the labels. You can see the labels and you can see their memory addresses. So for example, let us start here at var1. Okay, now var1 is the first thing that appears after .data. So therefore, the assembler is going to allocate, okay, memory in the data segment. Remember, it's the static area in the data segment. In the same order, the variables appear, okay, in your program. So I have var1. Now var1, it's actually here the directive is .byte. So here 1 will be a byte, 2 will be a byte, and we have the character Z here is also a byte. So we have 3 bytes. So if you look here, okay, suppose that the data segment starts at this memory address. Okay, so it has to start at some address in memory. Okay, that's the data segment. Okay, so therefore, first we are going to start here at this address. So we'll have 1. So we have 1 byte for 1. We have 1 byte for 2. And we have 1 byte, which is for the character Z in this order. Okay. Now, the label here is var1. And the address is this memory address. So in the symbol table, we place var1. And we place its corresponding memory address. Okay, that's the mapping between the label. The label is just a symbol that appears, okay, in your program. Okay, so this is just the name of a variable, and the address is the address of the variable in memory. That's really the idea. So it's a mapping between the label and between the address. This is why it's called a symbol table, because each variable name, it's called a symbol. Okay, so the label itself is just a symbolic, okay, representation for a given address. It's the address, it's not the value, it's the address. The address, it means that where this variable is located in memory. And we have not just 1 byte, we have 3 bytes, and these are their values. Of course, 1 will appear in binary as 8 bits because it's a byte. 2 will appear in binary, and capital Z will also appear in binary. Capital Z is a character that has a code. Okay, let us continue. Now, next I have ASCII Z, and this is a string. So M will be a byte, Y will be a byte, space will be a byte, and because we have Z here, we have ASCII Z. This string is terminated with a null card. So if you look closely inside the memory, you will find the bytes, okay, for that string. Now, str1 is the symbol, it's the label, that's the name, and these are the bytes. Now, you will say, what is actually the location of str1? It will come immediately after var1. So therefore, if var1 starts at this address, and we have 3 bytes here, so therefore we have to add +3 to this number. So this will be the address of str1. So this is computed by the assembler. So the assembler will allocate memory, okay, for these variables, is going to also to compute the addresses of these different labels. That's what exists inside this symbol table. So therefore, it would str1 will start at this address and then continue. Now notice that it has inserted one extra here, 0 at the end of the string. Notice that \n is just 1 byte, and there is a null character. A null character is a byte that has the value 0. Okay, that's automatically inserted by the assembler because you have used the directive.ascii z. This is following exactly the same convention which is used in the C programming language. Every string must be terminated with a null card. Okay, so it used the .ascii z directive to force that to insert an extra null character at the end of the string. Next, we have var2, which is a word. Now, here is the problem. Well, with bytes and strings, there is no alignment. They can start anywhere. But for a word, automatically the alignment is done. Okay. Now you can actually count. How many bytes do I have here? Well, let us count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Here I have 3, so I have 14. I cannot start at address 14 because 14 is not multiple of 4. 14 is an even number. It's multiple of 2, but it's not multiple of 4. 12 is multiple of 4. 16 is multiple of 4, but not 14. Okay. So therefore, I cannot start var2 at address 14 because it says .word. And by default, even without using the .align directive, by default, the assembler is going to align var2. So therefore, its address must be multiple of 4. So therefore, since we cannot start at address 14 and we cannot start at address 15 because these are not really multiple of 4, we are going to leave them empty and we are going to start at address 16. So notice that here, 14 and 15, these 2 bytes at these memory addresses. Okay, so we cannot start at 14 and 15. I'm showing here 16 bytes per row. These will be unused. And therefore, the address of var2 will be at address 16. So we add 16 here to this number in hexadecimal. Now 16 in hexadecimal is 10. Notice it starts here, it ends with 10 in hexadecimal. That's 16. Okay, I'm running out of time here. Okay, notice that this is a word. Now, according to the little endian byte ordering, okay, the little byte here, which is 7, 8, will appear first. Now, notice that this in hexadecimal, every 2 digits in hexadecimal will be a single byte. So here we have 4 bytes. So 7, 8 will appear first. I'm just writing it here just for clarity. I'm writing exactly the same way it appears. But if you would like to look at the individual bytes, 7, 8 will appear first, then 5, 6, then 3, 4, then 1, 2. I'm going to keep it like this as 4 bytes, just for readability. That's it. Okay. But the ordering of the bytes will be reversed. Okay, because this is little endian byte ordering. If it was big endian, then we start. It will be from the most significant to the least significant. But okay, so that's the byte ordering. So the alignment forces var2 to start at address 16. Finally, I have var3. Now var3 is a half word. It can start here. So this is 16, actually ends with 10. In hexadecimal, that's 16. So we need 4 bytes. So 4 plus 16 will be 20. So var3 can start at address 20 because it's a half word, and half word means it's even. But because we have used the .align3 directive, this is just to show you how we can use this directive, I would like to force the alignment of var3 to be 2 to the power 3. 2 to the power 8, 3, it means 8. So therefore, the address must be multiple of 8. Now, 20 is not multiple of 8, but 24 is multiple of 8. So therefore, we have to leave 4 bytes unused. Notice that this is the address of var2 here in the symbol table. I did not mention this. This is the address. Now, for var3, if we would like to find where is var3 in memory, we have to skip these 4 bytes because we cannot start at address 20, and var3 has to start here at address 24. So this will be actually here a half word that has the number 1000. Of course, 1000 will be in binary, and it occupies 2 bytes. It's a half word, 2 bytes in memory. And this is var4, and this is the number 24. 18 is 24. It's 16 plus 8 is 24. Notice that these addresses are shown in hexadecimal. Right. sorry about this. I took actually a few extra minutes to explain the symbol table. Okay, do you have any question about this? Okay. Okay, since you don't have any questions, so let me just here stop the recording. The next topic is about system calls. So I need to talk about system calls. I'm going to go back here to my highlighter. Now, system calls are necessary because programs have to do input and output. So the way to do input and output is to use system calls. And the MIPS architecture provides a system call instruction. So there is an instruction which is called system call. And this system call is going to interact, okay, with the operating system. So the operating system is designed, okay, to provide input and output, to provide services to running programs. So, so to obtain this service, the program has to execute the system call instruction. So since we are going to use a simulator, we are not really using a real operating system. Okay, so the MARS tool is just a simulator. It's going to simulate a number of system call services. But in reality, if you are running a program on a real operating system, let us say you are running it under Linux, or you are running it under Windows, or the Mac OS, or under Android, all of these operating systems provide services to applications. And the interface between the running program and the operating system is known as the system call interface. Okay, so when you execute a system call, okay, the processor is going to transfer the control from the application, from the program into the operating system. There is an operating system routine or an operating system function, okay, that will be executed by the operating system. And then once the operating system finishes the execution of this function, of this system call function, it returns back to the program. It's like making a function call. However, this function exists inside the operating system. Now, in order to do this, what you have to do is that you have to place the service number in a register, and this register must be V0. And then you load the arguments, if you would like, if there are arguments that have to be passed to the system call, these have to be passed in A0, in A1, and so on. You can have multiple arguments. And then you execute or you write the system call instruction. So once the system call instruction is executed, it's going to transfer the control to the operating system function. And then the operating system function is going to execute. And then once we are done with the execution of the function that exists as part of the operating system, is going to return back, okay, to the program, and then we continue execution after the system call instruction. Okay, sometimes the system call instruction is going to return some results. So if it returns some results, it's going to return them in V0. Sometimes it returns two results, it's going to return them in V0 and V1, depending, of course, on the system call function, okay, or service that you are trying to obtain, depending on the system call function. Right. So let us take a look here at the system call services. I'm calling them services here, but these are really functions. Okay, the first one is called print integer. So these are really simulated by the MARS tool. So the first one is print integer. So you have to put 1 in V0 before you can actually print. And then you have to put the value in A0. So this is the integer value that you would like to print. So you put the integer value in A0, you put 1 in V0, you execute the system call instruction, and it's going to print the value which is in A0. If you would like to print a floating point number, the value should be in F12. You can actually have single precision float or double precision double precision float. You use here the system call service 2 or system call service 3. So these services are defined by number, not by name. Okay. And then, for example, to print a string, okay, it is system call service number 4. Okay, so you have to put 4. You have to initialize V0 with the number 4. A0, in the case of a string, okay, the string does not really fit inside a register. The string will be in memory. So you place the address of the string. So the address of the string will be stored inside A0. So you store the address, or you load the address of the string, and the string must be null terminated. So it must be terminated with a null car, so that the print string knows when to stop printing the characters of the string. Because if it's not really null terminated, it's going to go on and on, okay, printing characters until it sees a null car, okay, a byte which has the value of 0. Okay, that's the null car, and we have to use the null car to terminate the string. Now we can read an integer, okay, using the system call service number 5. So the value will be returned in V0. You can read a floating point number. The value will be returned in F0. So F0 here is a floating point register. The same thing here for F12. These are floating. This is a floating point register. You can read a double precision. Okay, so the double value will be returned in F0. In fact, it's going to be returned in a pair of registers, F0 and F1, because a double will be 8 bytes. And if on a 32-bit architecture, if the floating point register is only 4 bytes, then we need a pair of registers to store the double precision floating point number. In the case of reading a string, we are going to type the string, okay, from the keyboard, and the string will be stored in memory. So A0 will be the address of the string in memory. So I'm calling it the input buffer. So it's an array of characters or an array of just bytes. Okay, and you store the bytes or the characters of the string. Okay, you store them in this array. Now A1 is going to specify the maximum number of characters to read. Okay, so this maximum number of characters is very important because you don't really want to exceed, okay, the size of the buffer that you have in memory that you have allocated for this input string. So if you reach the maximum number of characters, then this is the number of characters that will be stored, and the rest will not be stored. This is when you are reading a string. So if you have, for example, allocated 100 bytes in memory, you cannot really store more than 100 characters. And the last character must be terminated. So therefore, in fact, you are storing 99 characters plus 1 null character. So if the user enters more than that number of characters, then the rest will not be stored, will not be read, will not be stored in memory. Now, there is an interesting here, this system call service, which is service number 9. Okay, that is going to allocate memory dynamically in the heap. So here you specify the number of bytes that you would like to allocate. And then once you issue the system call, it's going to return the address in V0. Okay, so V0 will contain the memory address. So this system call is going to allocate memory dynamically in the dynamic area in the data segment. You can use system call number 10 to terminate the execution of a program. Okay, you can terminate this in any function. There are more system call services. Okay, so for example, print character is system call 11. So you specify in A0 the character to be printed. You can use 12 to read a character. So the value which is read, so the user is going to enter the character. He's going to type the character on the keyboard. And the character will be returned in register V0. Now, there are also system call services to open a file, to read from a file, to write to a file, and to close a file. Okay. Now, this is very important when you have your data in a file. Okay, so first you have to open the file. Now you have to provide here A0, which is the address of the null terminated string that specifies the file name. So the name of the file, okay, should be stored as a string. It will be in memory. So the address of the string that contains the file name, okay, so this address will be placed in A0. A1 will specify some flags, like, for example, 0 will be read only, 1 will be write only. A2 will be the mode. Okay, this is used on real operating systems, but it's ignored by the Mars tool. And then it's going to return the file descriptor in V0. Okay, and if there is an error, okay, to open the file, it's going to return a negative number, okay, indicating that the file cannot be opened. Otherwise, going to return a file descriptor. And then you can use this file descriptor. You can pass it in A0, okay, to read from a file, or to write to a file, or to close a file. You always use the file descriptor. So the file descriptor is just like an integer, okay, number, which is used to specify that you would like to read from it. You can open more than one file, by the way. You will get different file descriptors, and you can actually use these file descriptors to read from these files, or to write, or at the end you would like to close a file. So here what you have to do is that if you would like to read from the file, you are going to read bytes. So you have to have a buffer, an input buffer, which is just an array of bytes. And you specify the address in A1. You specify here in A2 the maximum number of characters to read. And then if the file contains less number of bytes, depending of course on how many bytes exist inside the file, if the file is actually small, then it's going to return the actual number of characters that were read in V0. Okay, the same thing actually for writing to a file. So you have to practice using these in the lab. I'm just explaining the meaning of these system call services. Okay, but you have to practice doing them by writing some programs in assembly language using these system call services. So the best way to do it is to practice, okay, using these okay, system calls in the lab. We're going to also have assignments that will MIPS programming assignments that will use these system call services. Here's an example about reading and printing an integer. So notice that I'm going to use here the system call 5. I'm using here LI, it means load immediate. Load immediate, it means that initialize V0 with this constant. So we are just loading this constant into the register V0. Now, 5 here, if we just go back to the previous table here, 5 means read integer. Okay, that's system call number 5, which is shown here. So I really would like to read an integer. So I'm going to actually place 5 in V0, or initialize V0 with the constant 5, and execute the system call instruction. Now, when the system call instruction is executed, okay, the program is going to pause, waiting for the user to enter the integer value from the keyboard. So the user is going to type some keys on the keyboard. These should be digits, decimal digits. There might be also a minus, okay, if the number is negative at the beginning. So once the user has typed the digits of the number, these are read directly from the keyboard. The system call service function is going to convert these digits into a binary number and store this binary number in V0. So the value which is read is stored in V0. So once this value has been entered, the user, of course, has to type enter. He has to press on the enter key. Okay, so once the user has finished entering these digits, that will be converted into these decimal digits, being decimal. The program is going to convert it, the system call function is going to convert it into a binary number that will be stored in V0. If you have a negative number, it will be in the 2's complement representation. Now, if you would like to print, okay, this integer, you have to move V0 into A0. So you pass the value of the integer in A0. You initialize. So here, notice that load immediate is going to initialize V0 with the number 1. Okay, so 1 here, if you just go back, it is print integer. And A0 must contain the integer value to print. So we copy the value of V0 into A0, and then we initialize v0 with 1, and I have another system call instruction. So this second system call instruction is going to print the value that was read, okay, by the first system call. And finally, if I would like to terminate the execution of the program, I can initialize v0 10, so, and then execute system call. So this will terminate the execution of the program. Okay, so very simple program, okay, that illustrates the use of system calls, how we read an integer and how we print an integer. Any question about this? If you have any question, you can raise your hand. I will see you. Right. I have another example, which is reading and printing a string. This is actually really more interesting. Now, notice that under the data, I have str. Now, that's, I would like to allocate space. So I'm using the dot space directive, space in memory, for the string, because the string cannot be stored inside a register. A register can only have 4 bytes, but the string can have more than 4 bytes. So I'm allocating here 10 bytes in memory for my string. I just use 10. You can actually have any number. You can actually make it very large if you want. You can actually have 100 if you want, or 1,000. Okay. So basically, what this dot space directive will do is going to allocate 10 bytes, okay, in memory in the static data segment for str. Str here will be just a label, and the assembler is going to construct a symbol table that will map str to its address in the data segment. Okay. So only 10 bytes have been allocated for str. As I said, you can change this 10. You can increase its size if you want to. Now, inside my main function, so notice that here .text, .global main, okay, .text indicates the beginning of my text segment, which is my code segment. This is where I have my instructions. And this is my main function. I would like to load the address. So LA here means load the address. str here, this is the name, this is my label. Okay, so I would like to load the address of str into A0. So the assembler knows that you would like to obtain this address from the symbol table, because remember that each label has a corresponding address in memory. Okay, so this is known by the assembler because the assembler has constructed a symbol table and it has mapped, okay, the label into its corresponding address. So therefore, we are going to load the address of str into A0. So A0 now contains the memory address. And I would like to place a limit on the maximum length of the string. So this will be in A1. So A1 will be 10, indicating that I only have 10 characters, 10 bytes in memory. I cannot really have a string which is longer than 10 bytes. Okay, so this will place a limit on the length, okay, of the string. Yani if the user types a very long string, which is more than 10 bytes, we are going to only to store 10 bytes. We cannot store them more than that. So that's actually A1. So we load here 10 into A1. That's the maximum string length. And I'm going to use here load immediate V08. So I'm going to initialize V0 with 8. This is service number 8, which is going to be used by the system call. Okay. Now, service number 8, if we just go back to this table here, 8 means read string. Okay. So read string needs the address of the input buffer, and it needs the maximum number of characters that were specified here. Okay, so the address will be str. Notice that I use load address. Okay, so it's going to be loaded into A0. And A1 here, this is the maximum string length. And the service number is 8, indicating that this is the function that we are going to execute as part of the operating system that will, okay, that will read the string. So when this system code is executed, the program is going to pause, waiting for the user to enter the string. Now the user is going to type the string. If the string actually has few characters, okay, less than 10, then no problem. Okay, then the string can be stored completely in memory. However, if the string has more than 10, it's going to stop after reading 10 characters. It cannot read more than that. Okay, because the space that was allocated, okay, for the string in memory is only 10 bytes. So it can store only 10 characters. Now, if you would like to print the string, use for here. Okay, this is the system call for, and okay, write the system call instruction. This will print the string. Okay, again, back to this table, print string only requires A0, which is the address of a null terminated string. So the string must be null terminated. Notice that here, when the string actually was read, automatically there is a null car who's going to terminate the string. So therefore, it uses this null car to stop. Okay, so to print the string, so it's going to stop at the null car. So if the string is, let us say, short, let us say less than 10. Okay, suppose it's only 5 characters, going to actually to print these 5, and then it's going to reach the null car and then stop printing the string. And then finally here we have system. This is the service number, which is 10. Okay, which is actually to exit, terminate the execution of it. So this is a second example about the use of system calls. I have a third example here about the sum of 3 integers. Clearly, I can see that nobody is asking questions, so I'm going to move fast. If you don't ask questions, it's actually fine with me. If you would like to interact, you are free to interrupt me and to raise questions. If everything is clear, that's fine with me. Right, so here I would like to calculate the sum of 3 integers. So I'm going to write a program that will ask the user to enter 3 integers or 3 numbers, and then read them one by one, take the sum, and then print the result. Now notice that under .data, okay, I have 2 strings. I have prompt here, .ASCII. This is a string which is terminated with a null car. Notice that I'm always terminating this with a null car. And the reason when I would like to print, okay, when I would like to print the string, we need to stop at the null car. So the null car is very important to mark the end of the string. So it's very important for the system call, because if you don't terminate it with the null character, then it will continue. Okay, so the first string is please enter 3 numbers. Okay, and this is terminated with a new line and a null car because of this ASCII DC. And the second, okay, it's a sum message, which is also the second string here. Okay, it's a sum message, which is the sum is. Okay, that's it, without a new line character, because I would like to print the sum, okay, as an integer after the string. So the first step is to print the string, the prompt. So I'm going to load the address of prompt into A0. It will be the address of this string. Okay, so the address is just a number. Okay, it will be the address of the string in memory. So we're going to load the address into A0. And then we're going to load the constant 4, which is an immediate in V0. Okay, and we have the system call instruction. So 4 means print string. So it's going to print please enter 3 numbers, space, new line character. So therefore the cursor, so the new line character will be printed, and therefore the cursor is going to advance to the next line. If you don't really want the cursor to advance to the next line, you can remove the new line character. It's up to you. After that, I would like to read 3 integers. So I'm going to use system call 5. So here, notice that I'm going to load immediate into V0. I'm going to load the constant 5. 5 means read integer. Okay, just go back to this table. So read integer, this is actually system call 5. So you have to have 5 in V0. Okay, so we are going to actually have load immediate v05 to read the first integer, system call. So the system call is going to wait for the user to enter the integer. Once the user types the integer and presses enter, then we return from the system call. The number will be converted, as I said, into a binary number, and this binary number will be returned in v0. So the result, or the number that was read, okay, by the system call function is going to be returned in v0. And you can actually just move it into t0, into a temporary register 0, because we don't really want to lose its value. I'm going to change the value of v0. But before changing the value of v0, I have to move the value of v0. That will be the integer that was read by the user. Next, we are going to read the second integer. So again, load immediate, okay, v05. 5 means this is the service number 5, which is reading an integer. A second system call. Again, wait for the user to enter a second integer value. Once the user has entered the digits of this integer, presses enter, then the system call is going to convert it to binary, is going to store it again in v0. So we're going to move the value of v0 into t1. Okay, so we save the second integer into t1. Repeat a third time. Another here load, okay, load immediate v05, and another system call to read the third integer. Notice I'm writing here comments. It's very important to write comments in assembly language to explain what you are doing. Okay, at least if you are writing something in the exam or in a quiz, and you cannot actually test or verify, at least you can explain to me what you are trying to do. So if you make a mistake, at least I understand your intention, okay, what you would like to do. So read integer, you have to use system call 5. You have to remember these system calls. And you have to write the system call instruction. So again, here the system call is going to wait for the user to type an integer. It's going to return the value of the integer in v0. So we move here v0 into t2, another temporary register. Now I would like to calculate the sum of these three integers. So I'm going to add t0 plus 2t1. I'm going to put the result in t0. Add t0 to t2, put the result again in t0. So I have added these three integers. Now what I would like to do is that I would like to print, okay, the sum of these three integers. So I need to write here some message. Before I print the result, before I print the integer, I'm going to print the string. The sum is, okay, so this is my sum message. Okay, this is just a label. Okay, so we need to load the address of this label into a register. So I would like to print the string. The string exists in memory, but I would like to load the address, okay, of this string. So here's some message. I'm going to load the address into A0. So now we have the address of the string in A0. I'm going to load the immediate here. So I'm going to initialize B0 with 4. This is for printing a string, okay? And then the system call. So the system call is going to print the string, okay? So it's going to print this string. The sum is, I would like to print it, okay? So after that, we would like to print the integer. So the result now exists in T0. So move T0 into A0 because we have to have it in A0. And then use here the service number 1. So load immediate V01. This is to print an integer and use the system. So this will print the final result, the sum of these three integers. And then finally, we terminate the execution of the program by using system call 10. Okay. Let me, go back here. Start. So go back here to the previous last slide. So that's it for today. This was my last example about system calls. Okay, maybe you have seen that in the lab. Maybe you are going to practice more, writing more programs in the lab. Do you have any questions? Any questions, students?
Doctor, I have a question. What is ADU?
What is?
ADU. Why there is U?
Okay. What is the U in ADU? Okay, good question. Now, the U here means add unsigned. Okay, so the U means unsigned. So there are two add instructions that exist in the MIPS. I did not talk about them. I'll come back to them, inshallah, in my next lecture. I will be talking about arithmetic. So add is an arithmetic instruction. It's just going to add two integers. There is actually two instructions. We have add U. So the difference between these two is that add can be used to add signed integers, and it can be used also to the difference between add and add U. Really, it's not about signed or unsigned. So the U here means unsigned, okay? But the real difference between add and add U is that add is going to detect overflow. So in the case when you are dealing with signed integers and there is overflow, then the add instruction is going to generate an exception in the case of overflow. Whereas add U, okay, even though it's there is an overflow, then the overflow will be ignored by add U. So here I would like to add these two integers, but I would like also to ignore overflow. What I said that just 1 minute earlier is that add U can be used to add the unsigned integers. It can also be used to add signed integers. But really the difference is that it's going to ignore overflow, okay? So I will talk more about it, inshallah, next week, okay, when I talk about the arithmetic instructions. And so the question is, do we care about overflow or should we ignore overflow? The add instruction is going to generate an exception if there is overflow, whereas add U is going to ignore overflow. This is why we have these two instructions, okay?
Okay, thank you.
Other instructions? I mean, other questions?
Doctor, do you have any quiz? Do you have a quiz anytime soon?
Okay, I'm going to actually post an announcement, inshallah, on Blackboard, okay, indicating when we are going to have our first quiz, which is related to what we have seen so far. So we had two lecture presentations. So we're going to have next week, inshallah, our first quiz. I'm going to announce it on a Blackboard.